Good afternoon, everyone. It's 1:02, so we will go ahead and get started. My name is Ed McMahon, and I'm the CEO of Epec Engineered Technologies. As many of you know, we're a 60-year-old company that designs and builds a host of different custom-built-to-print electronics. Over the last 5 years, here at Epec, we have developed a world-class battery technology division with our Engineering Tech Center located in Denver, Colorado, and our manufacturing facilities both here in Boston and in China. Leading that development has been our division manager, Anton Beck, and our presenter today, Randy Ebraham. Randy's been a leader in the battery and battery charger industry since the early 90s when he led the original initiative to create a smart battery and battery charger division as the CTO and VP of technology for ABT and Nexergy. As the founder of Precision Battery, Randy's work includes pioneering the development of custom safety circuits, battery chargers for lithium-sulfur chemistry, fuel gauging, and battery chargers for lithium-ion and lithium polymer chemistries. As a result of these efforts, Randy has received numerous patents for his area of work and has written numerous articles for industry trade publications. Over the past several years, Epec and Precision Battery have worked on over 50 different development projects in the medical, military, portable device, and industrial sectors, which then utilize our state-of-the-art manufacturing facility in Boston or our low-cost manufacturing facility in Asia. Before I turn this over to Randy, who will be presenting on new battery technology advances, I just wanted to give everybody a quick few housekeeping issues. First, if you have any questions during the webinar, rather than waiting to the end to talk about them, please go ahead and type your question on your webinar control panel, which is at the bottom right-hand part of your screen. At the end, we'll compile all the questions and we'll let Randy answer them. Secondly, we'll be recording this webinar like we do all the webinars, and we'll be posting on our website for future viewing if you so need to reference this in the future. And then lastly, if you have any questions after the webinar, you can, of course, always contact your Epec salesperson or send an email to our website, and we will get you an answer. So thank you again for taking the time to attend this webinar. We hope you find it informative. And at this point, I'll turn it over to Randy.
All right. Well, thank you, Ed, for the introduction. And also I want to thank everyone for taking time from their busy schedules before this holiday weekend to join us today. What I want to cover today are advancements in new battery technologies. To appreciate how new these technologies really are, I would like to take a quick stroll through history to put it all in perspective. We will also cover how and why these chemistries require electronic safeties and how they actually opened the door and provided an opportunity to add added value electronics. The added value electronics we will cover is essentially electronics that resides in a battery pack, but it's not required in its basic safety or operation. There are numerous added value electronic circuits that we can add to a battery pack. Too many to cover in today's discussion. However, we'll cover the most important and most common of these circuits, those being embedded battery chargers. These are battery chargers that are actually in the battery. Wireless battery charging, which has its limitations. System output power conditioning, which makes a battery not behave like a battery, but more like a power supply. We'll also take a brief look at fuel gauging and then wrap it up with showing some of the benefits of using general purpose IOs. I don't want to take much time on this slide, otherwise I may need to extend the timeline past the year 2200. But seriously, it is believed by some that the first battery was the Baghdad battery, and historians believe it was invented in the early centuries AD. It took another millennium to elapse before Mr. Volta announced his discovery of the voltaic pile, which is a simple battery made of alternating zinc and copper plates and using sulfuric acid as electrolyte. After almost a half a century, the lead acid battery came on the scene, which was the first rechargeable battery. And what is even more interesting, as you know, it's still in common use today, and it's probably one of the most common batteries out there. After many decades, the NiCad battery was commercialized in 1946, and this brings us finally to the lithium-ion battery, which has been commercially available for a little over 20 years. But during this time, there have been many spin-off lithium-based technologies with various capacities and desperately needed capacity improvements. The energy density increase throughout time is depicted in this slide. The blue arrow shows how the volumetric and gravimetric energy densities have increased with the newer battery chemistries. As you can see from this famous photo of a laptop battery on fire in a conference, there is a price to pay for continual capacity improvements. To achieve the capacity improvements we are seeing, more volatile materials are being used in the design of these newer cells. Newer commercially available lithium-based cells are actually quite safe when not subjected to conditions outside their design parameters. To guarantee that these design parameters are never exceeded or violated, electronic circuits are added to the cells to stop any external abuse to the cells. All lithium rechargeable batteries require primary safety circuits as a minimum. Cell balancing helps keep multiple series cells in line to improve runtime, cycle life of the pack, but also they help prevent the primary safety circuits from activating. Batteries designed for medical and IT applications require another level of safety in the event the primary circuits fail. These are referred to as secondary safeties. Since we now have a circuit board on the battery anyway, what else can we add to improve the performance and features? If we add enough features, today's batteries can now be viewed more as a power system or power supply than a battery. We will now go through each feature listed below, starting with the embedded battery charger. An embedded battery charger is a dedicated battery charger that resides in the battery and is normally not detectable by the end user. The battery just looks like a battery. With an embedded charger, unregulated or regulated power can be used to charge the internal battery from a number of various sources. These range from inexpensive wall bricks to cigarette lighter adapters, USB ports, even wireless charging pads. There are many advantages to using embedded battery chargers. They increase the battery life and safety. Namely, cells are always properly charged under all temperature conditions. The use of unauthorized chargers is unlikely to damage the battery. And also there's no need for more expensive external chargers. Also, there is a value perception that a simpler solution is at hand by the end user. Some of the disadvantages may be quite obvious. A couple of these include upfront initial cost of the battery is higher, and when the battery needs to be replaced, you're throwing out a perfectly good charger. Well, that's assuming that, of course, we designed it. Over the years, wireless charging hasn't really taken off, mainly since each company has proprietary type design. The inductive power standard, QI, has changed all that. Using inductive power standard, Epec can embed wireless charging electronics in your battery to work with a number of off-the-shelf charging pads currently available. If needed, we can design a pad to cosmetically match your product. There are limitations in power, however, so this is sometimes not always the best solution in all cases. An added feature that we can provide as part of an embedded charging solution using a wall brick or wireless charger is to power your product while the battery is being charged. In some cases, input power can be very limited using a small wall brick, a wireless charger, or USB type power. In these cases, reducing the charge current to the battery when the system is momentarily demanding more power is required, so the input power is not overloaded. We do this by having two current loops, which are shown in red and blue below. The red loop defines the total current the system and battery can use, while the blue loop defines the maximum battery charge current. As the maximum total current defined by the red loop is reached, the charge current to the battery is reduced proportionally all the way down to zero if needed. However, caution must be made not to draw more power than was defined by the red loop. this could still overload the input power supply. Another nice feature that can be added to your battery is to regulate the output. All chemistries have a voltage slope as they discharge. The slope lines in the graph below shows the discharge voltage of a lithium-ion cell under various loads. This will also vary with temperature. Most lithium-based chemistries have a fairly flat discharge slopes, and normally systems can handle this variation in battery voltage. However, some can't, especially at the end of discharge when the voltage is the lowest. The blue dashed line represents a regulated output voltage that we can supply. In this example, we regulate the output to be constant 3.3 volts regardless if the battery is higher or lower in voltage. Taking the concept from the previous slide, we can take the regulated output voltage a step further. Sometimes we are replacing an older battery chemistry with a newer lithium-ion battery. A lot of older systems use a voltage-based fuel gauge to determine when the battery is close to being fully depleted. Since this form of fuel gauge is designed specifically for an old chemistry, it does not work with lithium-ion batteries and will give false fuel gauge readings to the end user. We can overcome this by having an onboard lithium-ion gauge adjust the output voltage of the battery to reflect the old chemistry's voltage profile, which makes the older system believe an older battery is being used. This is shown in the graph below by dropping the regulated output voltage slightly at the end of discharge. There are a lot of variations on this concept that can be implemented. We could spend hours talking about this fuel gauging, which is why I need to keep it very short. It's a long subject all on its own. State of charge can be determined by measuring the battery voltage and comparing the reading with an internal lookup table. Also, Coulomb counting can be used to measure all the energy entering and leaving the battery. Or a combination of both can be used to help correct the other's readings. This approach is great if your battery never ages or is ever exposed to temperature variations, which is very limited and very unrealistic. TI is the leader in simplifying the very complex nature of fuel gauging and has invented the impedance tracking fuel gauge. It is we have a couple hundred parameters that we can program to make the fuel gauge accurate within 1% throughout the life of the battery if needed. As shown in the picture below, a product that we developed, we can display the charge level using LED indicators or just send the data via a two-wire interface port. The last topic to cover is the general purpose I/O. These can be used to control any battery, subsystem, or control the end product functions using simple two-wire interface. We can adjust battery charge current, which is handy if different size cells are used in different SKUs and you don't want to make hardware changes. LED indicators can be activated, deactivated, and they don't need to even be battery related. They could be system related. Automate production built-in tests can be performed during production, which essentially can make more thorough tests of the product, either the end product, also the battery. So there's a lot of flexibility there. We can read internal hardware status indicators. These could be even signals from the provided embedded charger then sent to your system. The GPIO can be used to activate or switch over multiple battery packs if used. And it can adjust onboard voltage regulators as needed by the fuel gauge or the end product, which we saw a couple of slides back. And it can be used to activate a pyrotechnic self-destruct device, which can be used to actually protect sensitive IP, which, as it sounds, it will actually physically destroy the hardware. We've done this in military drones in the past. To summarize, today's batteries can offer embedded electronics, which improves the safety, reliability, cycle life, and functionality of the battery while giving the end product system engineer more options to make the end product more reliable and user-friendly. With embedded battery chargers, batteries last longer by charging them to their ideal specifications and only within the proper temperature limits. With accurate fuel gauges, batteries can be discharged to almost empty now with confidence. Hence, batteries do not need to be oversized, making them smaller, lighter, more dependable. And GPIO interface may provide access to information or functional control you had never thought possible. Here, again, imagination is the only limit. I'd like to hand it back over to Ed to cover some other products that Epec provides.
Great, thanks, Randy. And we're going to just compile some of the questions that came over during the discussion here. And while we're doing that, we'll just kind of go over quickly some of the other products. Many of you know that we do printed circuit boards and flex and rigid flex printed circuits, along with custom battery packs and many other of the custom built to print products that you see there. We recently have had a webinar on flex and rigid flex circuits that's on our website, and we will be having one on fans and motors here probably in the next 2 months. So please check out our website to see the previous webinars and any future ones as well. So having said that, Randy, would you kind of go over some of the questions that we've gotten so far during the webinar?
Okay, very good. Yeah, in fact, a couple of them came through here. One of them, it's kind of interesting, and in fact, we usually get this quite often. The question is, how much does fuel gauging add to the cost of my product? Well, this varies depending on the accuracy of the fuel gauge required and, let's say, the overall size of the battery pack. Maybe a good example, if a very accurate gauge is required on a small multi-cell battery, it could potentially almost double the cost because the cost of the cells are very small with respect to the added electronics. On the other hand, at the other end of the spectrum, let's say perhaps a less accurate gauge is required on an electric bike size type battery. It may only add maybe 10% to the cost because the overall cost is in the cells, in the energy density of the actual battery. Every application is different. If the cost is a driving factor, we can offer trade-offs to keep the cost to a minimum while offering a solution to meet your needs. So let me take a look here. Okay, and we got another one coming in. Let me read through this. Okay, yeah, this one's actually two questions. Someone's cheating here. How long does the output, let's say, how long does the output voltage have to drop to signal an older system of a low battery condition? And are there other ways of signaling a system of a battery condition? Looking at to answer the first question here, the length of time will vary depending on how the original system interprets a low battery. And if, let's say that perhaps there might be a low pass filter in the system, and which may vary or impede on detection time, we can work closely with your engineers to help determine the best signal to give your product by characterizing your end product and stimulating stimulus and a response here. Let's see. Then on the second question, I'll go ahead and repeat that one. Are there other ways of signaling a system of a battery condition? Yeah, actually there is. We've done a couple of these. Really, the sky's the limit on how we can signal your system and what your system can receive. The easiest way would be to use a 1 or 2 wire communication interface. If that's not available or possible, we can send simple signals via the output voltage by varying it slightly without disturbing your system with a known pattern. And this can change depending on what signals are being sent. So there's a lot of different things we can do there as far as especially making a product backwards compatible. And I think we got time. Yeah, time for another here. The this one here, let's see, read it real quick. Okay, doesn't an onboard battery charger add a lot of heat to your battery? Well, Yeah, they do if they're designed incorrectly. We've actually seen that with some of the competitive products out there, and which you need to be sure you apply this technology correctly. We also apply highly efficient synchronous switchers, ones that are put out very, very low heat for the amount of energy that they actually transfer in all our designs. We add thermal barriers in our designs to help spread the heat evenly to minimize thermal gradients within the battery pack, which, if ignored, can be very detrimental to the battery safety and cycle life. And I think that's it for the questions. So,
Randy, I appreciate it. We have a couple more questions. Unfortunately, I think that we're running out of time here. So, for those of you that have sent questions in that didn't get answered, Randy will go ahead and answer them and via email and send them back to you here this afternoon, because there's a couple more that are out there. So I appreciate everybody taking the time today. If you have any other questions, on Randy's screen there's our sales email that will be happy to answer any additional questions. But again, the presentation will be on the web probably by Monday, and you can go on there and either copy it, view it, do whatever you need to. If you need any additional information on anything that Randy's discussed, please get in touch with us. We'll be happy to go into it in much more detail. So thanks again, everyone, and we appreciate your time and look forward to seeing you on another webinar.
Thank you.